The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back. This is Sebastian. I'm flying solo again this episode. This is the second episode that I recorded while I was at the Rensselaer Polytechnic Institute launch event for their IBM System One quantum computer, which they deployed on the campus there, first university in the world to have an on-premise quantum computer. And after last week's panel discussion, which was on the Wednesday night of that week, I lined up a bunch of individual interviews with attendees, and this is the first of those conversations. So in this episode, you'll hear an interview with Olivia Lanes, who is with IBM Quantum. She's the global lead for education and learning. She and I actually overlapped at IBM Quantum, so we worked together there for probably a little over a year before I left for Amazon Web Services. And she's still leading those efforts at IBM. She's got a tremendous background. She's an experimental physicist by training, joined IBM, was working in the labs there at IBM Quantum, and then transitioned during the pandemic to leading the education and community building efforts there. IBM has been a real leader in education and workforce development and community building right from the very beginning when they open sourced Qiskit, and then soon thereafter created Qiskit.org as a sort of hub for the community and education efforts around Qiskit. So they've really been a leader. They've been trailblazing for quite some time and setting a great example for the other vendors in this space as it develops. And this conversation with Olivia is quite enjoyable. We get into a bunch of topics around what the challenges are for training resources, education. We get into how important diversity, equality, and inclusion is in this space. And we talk a bit about her own personal journey into quantum computing and the position she's in today. So I think you'll enjoy it. Let's have a listen. Joined today by Olivia Lanes, who is the global lead for education and learning with IBM Quantum. It's great to have you with us, Olivia. How are you doing?
I'm great. Thanks for having me.
Thank you for joining us. If you want, Olivia, it'd be great to get a little bit of an introduction and a little bit of insight into how you ended up in the field of quantum computing.
Sure. So my background is in experimental quantum physics. So I did my PhD at the University of Pittsburgh, and I studied quantum limited amplifiers and made a whole bunch of those for 6 years. And then when I graduated, my transition to IBM was really pretty smooth. People always ask me, what was it like transitioning from academia to industry? But when your transition is literally you doing the exact same thing in one building versus another building, it's really pretty easy. But then there was the pandemic, of course. So
Yes.
When the pandemic hit, we had some conversations about my role shifting a little bit. And then that's how I got involved in the community and the education part of it. Because I wasn't
Right, the labs shut down.
The labs didn't completely shut down,
restricted.
but I wasn't being brand new,
Right.
and needed personnel.
Yeah.
So I was also on Abe's team, who was leading the education effort back in the day. And he said, why don't you just focus on that for a while? And I said, great, I love this stuff. That's fine. I can't go to the labs anyways. And then I just did that for a few years and worked in the lab in my, free time, basically. But I ended up getting promoted and really following that course instead.
Right.
How I ended up here, It was just an accident.
Yeah. That's what most people's answers boil down to.
Yeah, if you really look at it, like, this was not the plan. I call myself a failed astronomer. Like, that's what I wanted to do. That's what that was the plan, was I will be the next Carl Sagan and I will go study astronomy. And what happened was I did an internship and I actually attempted to study astronomy, and I was like, oh, I don't like it. What do I do now? So this is plan B.
Right. Yeah. I can't remember if it was either Ken Brown or Dave Bacon. One of the two of them said that they consider themselves a failed chemist. So
yeah,
you're in good. And like I said, almost everybody's story does distill down to that. And that's kind of, in a way, I think that's kind of the challenge around the education in this field, is like there isn't a formal path, but then again, even sort of careers that do have formal paths, people end up falling into them anyway. You sort of have to plan for serendipity in a way.
You kind of do, and that's why I always feel very self-conscious when people ask me for advice and they try to, emulate my footsteps. I'm like, no, don't do that. It worked once for me, and that was it. Like, you don't want to plan to do what I did. You want to be a lot more deliberate and smarter about it.
Yeah. And I guess in a way that's sort of the differentiator between like training and education, right? I mean, training is sort of a more defined, like you need this set of skills in order to do X, Y, and Z, whereas education is like, I don't know, find a bunch of stuff out and try things, and you'll find, if you keep applying yourself, you'll find a way to do something interesting.
Right. I think that's a really good message too, because like when I was in high school and undergrad, it started to become a career that you could consider doing, on purpose when I was in graduate school. But when I was in high school and undergrad, like this was not a viable career path.
No.
But now it is. And now that I go out into the world and do a lot of outreach and talk to these people who are all trying to do the field that I did, but on purpose, it really has just been like 180 degrees in the way that I've been thinking about it.
Right.
Because it really just shows how the landscape is just so different. And I mean, I'm not that old. It hasn't been that long. I graduated like 10 years ago. So that's not that much time in the grand scheme of things.
No, and the field changes so quickly too. I mean, it feels like ages ago when I got involved, and it's only 7 years now, really. So, and so much has changed. Yeah. It's really incredible. Well, you definitely did. You are following in Carl Sagan's footsteps in one regard, which is you're becoming much more of a public spokesperson for the field.
Yes.
So in that way, you're definitely still on that path. How is that like? What's that like? I mean, you're quite a well-known personality on YouTube now with relation to quantum computing and
small niches
explainers.
Only.
Very small niche. You're a micro celebrity, yes. Yeah. But still, I mean, does that make it easier in some ways to sort of get sort of messages across to drive like educational agendas, or does it get in the way, or what's that experience like?
I think it is very helpful. Usually, like in regards to talking about like education and workforce development, I think people do tend to trust what I'm saying. But I think, one of the problems that all science communicators have, and Carl Sagan even had this problem, is people are like, well, are you a real researcher? Because if you're up here doing this, you can't possibly be doing real science. So why should I listen to you? And I do get that kind of sentiment every once in a while. But of course, it's always you just have to laugh at it at some point, because it's like, okay, random YouTube user 13567. I'm sure that you know this stuff way better than me. I'll just shut up.
I've seen you employ some very adept jujitsu on Twitter trolls as well, so it's very well done.
I'm sure my bosses really appreciate that.
Well, I'll say it is never, it's never aggressive. You're never crossing any lines. You're just sort of very gently pointing out the idiocy of the person coming at you. So
I want to
gentle.
Teach. I always want to teach. I never want to come across as being a jerk, but every once in a while, I got to stand up for myself a little bit.
Absolutely. You used the phrase workforce development, which is frankly something I hadn't encountered before getting involved in the quantum field. It makes a lot of sense, because if this is a disruptive technology with sort of broad impact across a number of different industries, we're going to need people who know how to do it.
Yeah.
But I mean, I guess, like, how do you see, because there's a bunch of different categories of workforce here. There's sort of people who could work at IBM, at TJ Watson. There's people who could work at, in an industrial R&D setting for a pharma company or whatever. And then there's the sort of broader set of skills as the technology becomes more capable and broadly distributed.
Yeah.
How do you sort of deal with those types of priorities, I guess?
Yeah, that's a really good question. So, like you pointed out, it's really a multifaceted problem. So priorities, I work for IBM, so I guess one of my priorities has to be to make sure that we can hire people, and as a hiring manager too, like I want to make sure there are people that can fulfill jobs that we're trying to hire for and that have skills to fulfill the needs that we have. I mean, that's a top priority, but it's not just for IBM. Like, we really do believe that other industries and other companies are going to have to succeed if we're going to succeed as well. So it's really about growing the workforce for all of these places. But like you said, the conversation is just so multifaceted. Do we start educating people more in quantum at the undergrad level, at the high school level, at the middle school level? Do kindergartners need to know what quantum is? Oh, but then we don't have enough postdocs. It almost feels unsolvable because there are so many different problems that we have to solve. But I'm just so fascinated by all of these questions. Like those are the problems that keep me up at night that I want to work to solve. Yeah. So, we're never going to be perfect, but hopefully we will asymptotically approach some solutions as one does in science, and that'll bring about, better change. We hope. We hope.
I could make a dumb joke about using a quantum computer to solve the problem. I won't do that. But I should say also, you mentioned Abe. Abe and I, you and I crossed paths at IBM for a time. Abe and I worked together when he and I both were new to IBM Quantum and started like the open source textbook and some other early education efforts. And the way you just put it was the thing I always appreciated about IBM's attitude towards this, which is that it's not just for the benefit of IBM. I mean, I thought that the amount that IBM has invested in education and workforce development for quantum has been a really good example for the rest of the industry.
Yeah, we certainly don't want to be the only pillar of quantum education. I mean, IBM has invested a lot. We've hired people like myself, specifically to work on this. But, I mean, it doesn't have to be the case that we're the only ones. Like, we welcome other people to join us in this endeavor, too, because, a high tide raises all ships, as they say. Is that the expression?
Something like that. I'm not a mariner, so I can't be certain, but that sounds right.
Yes, me neither.
Yeah, that's awesome. And, you mentioned as early as middle school, we've both been involved in Q12, which is an NSF-funded effort out of, I guess, UIUC and University of Chicago initially. I guess Emily is now at Duke.
She's
so I
at
guess,
Duke now, yes. Congrats to Emily.
Congrats to Emily. That's a terrific project that's sort of collecting resources for exposing kids earlier and earlier, sort of fundamental STEM concepts. You're not going to talk about qubits necessarily in grade 8, but you might talk about, photonic polarization with a demonstration of lenses 100%. And stuff.
People always ask me, is it really necessary to talk to middle schoolers about qubits and quantum computing? I'm like, well, no. Is it necessary? No, it's not necessary. Like, they will live just fine. Yeah, it's cool. But like, the other thing is, like, if I had to devise some sort of presentation for middle schoolers, I don't even know if I'd use the word qubit like you were saying. I might just try to show them something or talk a little bit about, entanglement or superposition. Like, my philosophy is, at that stage, before they're ready to like do any of the math that will solidify like a philosophical understanding, all you have to do is blow their minds.
Yeah, exactly.
Like, that's it. It's sort of like a magic show.
Yeah.
Like, where you're like, poof, and then the rabbit appears, and it's like, all right, I'm out. And like, if you can just confuse them, because middle schoolers and high schoolers think they know everything. Right. If you can just confuse them and show them that they don't actually understand the world as much as they think, this will annoy them and they will come back. Right. I swear they will.
Yeah. That's sort of the nature of human curiosity. Is like, I didn't get that. I'm going to try it again.
I mean, that could be my whole story too.
Totally.
Like, physics was my worst class in high school. And I was like annoyed that was the one that I didn't do well on. So I was like, I better go get a PhD in that, I guess.
That's hilarious. And it does, I mean, it feels like, people talk about sort of the problem in STEM education as being one of like a bigger funnel. And especially when you talk about, diversity and inclusion, a bigger funnel, but then also a less leaky pipeline.
Oh, yeah. We
as
have
you said,
super
all the way
leaky pipeline.
Yeah.
I mean, the funnel, to me, like, that's great. But, like, those are hollow words unless you fix the leakiness issue.
Yeah.
So, yeah, I mean, those conversations are all well and good, and we have them a lot. Like, how do we fix the funnel? How do we attract more people? But the conversations I'm more interested in are, like, how do we promote the people that are already here? How do we make sure that they're happy? Like, have you talked to the senior managers in your company lately? Have you asked the people who have been here, like, a few years, how their career is going, how they feel like they've been treated by peers? Not implying anything bad, but those are the more important questions, I think.
Yeah, I totally agree. And I think you're absolutely right. It's not, those conversations aren't an implication that something is going wrong.
Right.
It's an implication that they need to be top of mind so that something does not go wrong.
Exactly. Like, they should be proactive instead of reactive.
Yeah. Yeah.
And I would like to see more people do that, across the board. In academia and industry, it's not, an isolated problem, as I'm sure we all know.
No, it definitely isn't. Let's just keep our scope to STEM and more narrowly quantum, because we're not going to fix the rest of society's problems on this one. It's only 30 minutes, Olivia. So,
well, how much time do we have left?
like I don't know, 12 minutes.
All right,
15
we won't
minutes?
fix all the
Not
problems.
all of them, no. All right, climate change. No, never mind. So yeah, I guess next question I had for you, like, what do you see? This is sort of going to the sort of the collaboration side of things. What role do you see international collaboration playing in sort of this broader? I mean, again, sort of, talk about diversity. You've got a concentration of sort of access to resources in wealthier nations, which tend to be more northern hemisphere. So people use the term global south often as indicative of populations that have less access. Is that something that we can help fix with more international collaboration?
Yeah, I think so, for sure. I mean, we have made as much as we can make free and open access. Yeah. When I say we, I mean the IBM team, not me alone specifically, which I think is great because we've been able to see the geographic population of people who are accessing the systems and, completing their first lesson really exploded when we did that, which I think is great. But in terms of other international collaborations, I think they're a huge priority. One thing I've noticed is that certain countries and certain geographical regions, even in the United States, but, more broadly across the whole world, like there are pockets of people who specialize in really specific things in different areas of the world. And it just really brings into the whole conversation about quantum mechanics and quantum computing being a really interdisciplinary field. And since we need all of these different types of brains and minds and backgrounds to complete our mission, I would say in some ways, I think the collaborations that we have with all of these different pockets of specialties across the globe is what's going to enable our success.
Interesting. That's funny. We were just talking to Martin Savage from University of Washington a couple of weeks ago, who did a great experiment on the IBM system over the Christmas holidays.
Yeah.
And he said that he thought that quantum information science would become more of almost a lingua franca, like a universal language for physical sciences over time, because the toolkit, as these devices get more and more capable, the toolkit's going to be so powerful, whether you're talking about chemistry or, biology even, that quantum information science will just sort of be like part of the standard approach to these fields.
I think we're sort of like on the precipice of that right now. Like a lot of the conversations that we're having are, how much can we abstract away and how much do I really need to learn to use this?
Right.
And in the past, maybe even 2 or 3 years ago, I'm going to be like, well, you're going to have to learn some quantum physics. Sorry about that.
Yeah.
Good news is it's fun.
Yeah.
Don't worry. But now we're getting to the point where it's like, yeah, you should know a little bit. Like, you need to know what gates mean, and it's helpful to visualize the block sphere, but, like, you don't actually need to know what a transmon is at this point.
Yeah.
You don't need to know what a superconducting qubit is. You don't actually even need to know what architecture you're using.
Right.
And that kind of blows my mind a little bit, just because you don't normally see that level of abstraction this soon. when you're building a
right.
new technology.
Yeah. 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 It's sort of, I mean, I always think of we're in sort of like whatever the period of classical computing that roughly equates to like the 1950s or 60s, sort of, somewhere between the transistor and the monolithic solution. We've got microprocessors, except that we also have the cloud and GPUs and open source software and all this incredibly sophisticated
I know.
technology.
It's kind of funny because like all the really sophisticated technology is actually the classical part right now.
Yeah.
I mean, the cryogenics, that's been around for decades.
Yeah.
Like it looks cool, don't get me wrong, and like we should totally use that to like lure people in, but it's not new and it's really not even that sophisticated. It's like a bunch of plumbing parts.
Yeah.
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 But it's shiny, so people are like, this
It
is the future.
It draws the crowds. I remember the first supercomputing conference that we brought the chandelier to, and there were more people around the IBM booth than any other booth in that show because it was very, very interesting looking. Okay, cool. So, well, I should mention, we're at RPI, Rensselaer Polytechnic Institute, on the occasion of the ribbon cutting ceremony for the new Quantum Center, which is centered around an IBM Quantum device, which is on premises. What is your view of what the sort of educational opportunities, this is the only university with an actual quantum computer on its campus. It's in the middle of a beautiful building that you can walk in and see, as you were saying, the shiny object is right there in front of people. What do you see as being kind of the opportunity here educationally for them?
Well, there's a few, very boring but tangible things, which I'll mention first, which is that when you have an on-premise system, you don't have to wait in line to use it. Like that is your school's dedicated system.
Right.
And if you're trying to do something, you don't have to wait in the queue. And sometimes those queues can really pile up.
They can get really long.
So, that's a boring answer, but that's another piece of the puzzle.
It's practical, I think I'd say, yeah.
But the other piece of it is that I really do think it brings something intangible to just the vibe of the overall educational landscape. Like so many of the professors, so many of the faculty that I've talked to, and the students too, are just so excited about this. And that level of excitement is something that you can't buy.
No.
And you can't just install in your class.
Right.
And, it's cool that you can run simulations and you can send jobs to real quantum computers over the cloud. Like, I still think that's really cool.
Me too.
I probably don't appreciate how cool it is on a daily basis, but if you really sit and think about it for a while, it's cool.
It's really cool.
But it's not as cool as seeing it in real life and being like, I just sent my job to that machine.
Yeah.
And I also think being able to visualize it and, like, see all of the parts and all of the pieces brings a more fundamental understanding than you could possibly have otherwise. Because no matter how many pictures of the system that I show you, it's just not going to feel as cool as when you see it in real life. It's just not.
No, I saw it this morning. I can attest to the fact it looks really cool in real life.
Yeah. Oh, good. I haven't seen it yet.
Yeah. I got the VIP tour this morning.
All right. Sebastian's a VIP. I'm not.
But yeah, I agree with you. And I guess the other aspect I wonder about is, Rensselaer's known for being very advanced in their HPC and their supercomputing cluster. It's sort of been, a close partner of the power systems team within IBM for many years. They've done a lot of really cutting edge things here. And I wonder about having that kind of HPC culture and this on-premise device, whether that sort of affords opportunities for experimenting with, the physical deployment architectures, because these things are going to live in regular data centers eventually.
Yes,
right?
I think it will definitely offer the opportunity to do that. We have, another team that's very focused on the HPC thing as well. And then another thing, that I'll point out is that RPI, they have a strong physics and computer science department, no doubt about that. But they're so strong in all STEM fields and tech subjects. And one of the really cool things about working with RPI over these past few months is that I've gotten to talk to faculty from all different schools, which is something that's really important to me because I always say, physics has been hogging the quantum and we shouldn't let them do that because quantum is really the underlying physics of every subject. And I'm very big on we need interdisciplinary minds to solve the problems that we have. So I think it'll be really cool in terms of just recruiting and studying things that we don't normally get to think about.
Yeah. Well, and in a way, back to sort of the training theme, like I think the whole industry, quantum industry, has been challenged by, how do you get people to think in terms of these quantum information technologies enough, people from industry, so that they bring forward sort of the problem statements that can turn into use cases over time, right?
I mean, that's the hardest part. Like, unfortunately, whenever I talk to clients and students alike, the hardest part is the first problem. Unfortunately, that's how it is with quantum computing. The hardest part isn't the last step like it is with a lot of technologies. The hardest part is the first step here, which is identifying a good problem which could have real solutions based in quantum technology. Right. And people are like, well, how do I know where to start? I'm like, excellent question. You got to talk to a theorist.
Wish I had an answer. Yeah. So back to your point, I mean, I feel like because there's such a diversity of STEM strengths here and this quantum resource, there's almost a breeding ground for those types of interactions that'll lead to those problem statements that can turn into real use cases.
I hope so. And,
me too.
Hopefully we can identify some more use cases as well, because, we know, there are some in chemistry. We all are aware of that. We know there are some in finance, and crypto as well. But are there more in, the biology space? And the information science space, and I don't know, other STEM fields I'm forgetting that we're not focused on. We haven't really been dedicating enough time and resources to, because it's such a big space. It's hard to know where to start and where to divert most of our efforts to. So, like you said, I think there's opportunity for real synergy here. Yeah, totally. And I mean, it also, I mean, you said physics has been hogging the quantum. The reality is, I mean, I like to tell people that Feynman's sort of prediction or statement that if you want to simulate a quantum system, you need a quantum device, that we're at that stage now, right? There's now novel science being done on these devices that is a simulation of a quantum many-body problem at some scale that is very, very difficult to do, if not impossible, classically. We're right on the cusp of that. We're right on the cusp of that. Yeah. And one way that I've described it to people is that, in a few years, all computers that are not quantum are going to be a sad approximation of a computer, because physics and nature behaves quantum mechanically. It doesn't behave classically. So if you're going to try to simulate quantum phenomena on a computer that doesn't understand that, you're not going to get it. Right. It'll be an approximation. And in a way, physics has been hogging quantum because that's where, those are the people who are thinking in those terms day to day. Yeah. But once this becomes a toolkit that you can use in other domains, it may be that we find we can map all kinds of different problems at some level to some kind of quantum simulation. Yeah, and there are, hybrid classical quantum algorithms as well. I think that confuses people because they always ask me, which one is going to win, classical and quantum? And I'm like, that's not the right question to be asking. They're always going to play with one another. Right. And it's just, how much are we going to divert to each resource, you know? Right. We don't know yet. But, when you use a supercomputing cluster, you don't specify what rack you send your job to. Yeah. It'll just do that automatically at some point. And at some point, our software stack will be intelligent enough to be able to divert the problem to whatever hardware cluster is more aptly suited for your problem. Yeah. Yeah. So neither is going to win. Right. We are the winners. Yeah, exactly. Exactly. Not the machines. Not yet. Hopefully. Okay, so we've gotten a little off of the main theme of training and education, but I like that because I wanted to actually swing around to almost more of a personal dimension here, which is, you said you started building quantum filters, and on the experimentalist side of things, you've had this foray into training and education. Do you see yourself getting back to experimental physics at some point? That's a really good question. I don't make a lot of predictions at this point in my life anymore is the honest answer. So I don't know exactly what the future is going to hold, but I have to say I'm loving what I'm doing right now. And there are so many good experimental physicists in the world that I'm not worried that like my leaving would leave a vacuum of any kind.
Well, it would on the training and education side.
I don't want to like toot my horn too much, but I do feel like that is sort of where I've found a need for right now for the specific skills that I have.
Yeah.
So for right now, I don't think I'm going to venture back into the lab anytime soon.
Good. Could we need more explainers, Olivia?
I love explaining things.
I know.
And I think
you're very good at it.
Thank you. I think it helps that I had a technical background. I certainly don't regret getting my PhD.
Right.
Not that it was like all, unicorns and rainbows, but I think it helped me learn to think in a way that helps me explain things better.
Awesome. Well, it has worked. Okay, so last question then. I'm going to steal the Ezra Klein thing. What are 3 resources that you would like the listeners to go look up for learning more and taking the next steps in quantum computing?
Oh, 3 resources. Okay.
Yeah. He usually says 3 books, but that's not applicable here. So.
3 books or resources.
Yeah.
Okay. Well, I think the first one I'd have to point out is the learning platform that we've created on the IBM Quantum site, because I really do think it is a good source of information. We put a lot of work into it. It's not like done now. It's a living document. So if you are logged on, you're like, I've already taken all of these courses. Like, don't worry, just visit in like a month or 2. I'm working very hard to populate it with more material. But we were trying to make the quality, top notch. So it takes a little while. Another book that I really like for beginners is Tom Wong's book. I plug that book a lot. I forget the exact title. It's like Understanding Quantum Information, I think. But I think it's free online, but I bought a copy also really cheaply off Amazon too. And I think that if you're trying to understand like the statistical nature of things and you're not used to thinking that way, the book is really, really great for that. And then I don't know. I might just say YouTube for the last one.
The Qiskit channel is pretty rich.
We put a lot of stuff there. I mean, I could say like Nielsen and Schwang, but
I did say resources, so YouTube channel is definitely allowed.
You can learn so much for free if you know where to look. The only thing, I'll caution people who are online trying to create their own solo learning experiences, so make sure you're not listening to somebody who has no idea what they're talking about.
If anybody says do your own research, don't.
Yeah, it's such a loaded statement. There are so many nuances with that. It's like you should do your own research, but you have to know how to do research first. And that takes like 15 years.
Yeah. Yeah.
So,
well, I think the Qiskit channel is a really good example of well-curated content. So, I mean, anything you watch on that channel, you can at least trust it is fully vetted. It's coming from people who know very well what they're talking about.
That's true. I promise.
It's super, super useful.
There are opinions. Opinions are not necessarily fact, but I am not. There are no falsehoods.
Right.
Yes.
Right. Yeah, and actually, Zlatko is still doing his Friday seminar series, I think, too.
Yep.
That's what actually got me thinking about doing a podcast originally. So.
Oh, Zlatko's seminar? Yeah.
Yeah,
those are really good,
They're
too.
terrific, yeah. Well, great. Awesome. Thank you so much for joining us, Olivia.
This was so fun.
A great conversation.
That conversation. It was great to catch up with Olivia. I hope you enjoyed listening to it. I think workforce development and education and training in the quantum computing space is a really vital topic for us all to pay attention to. I hope that if you are in the process of learning more about quantum computing, you have been finding the resources that you need Actually, I highly recommend the resources that Olivia mentioned, IBM Quantum Learning Platform, the book by Tom Wong, the Qiskit YouTube channel. There's tons of other resources out there, lots and lots of free stuff, great organizations helping people learn. And thanks again for tuning in. Thanks to Olivia Lanes for joining us, and we'll see you next time.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.